you ever tried painting your bike? It can be a really messy job, especially if you use wet spray paint. It's hard to get a good even finish, and most of the paint ends up on the floor. Rachel's painting her bike with powder, using static electricity. Dead easy, but how does it work? This polythene rod is charged with static electricity. It attracts things. The rod gets charged by rubbing it with a duster. Here's what happens. Inside everything, there are millions of very tiny particles called electrical charges. There are two kinds of charges, positive and negative. Usually, each positive has a negative partner. But rubbing things together can separate the charges. In this case, some of the negatives moved from the duster onto the rod. Once you've stopped rubbing, the charges don't move around. That's why it's called static electricity. The rod now has more negatives than positives, so it's negatively charged. The duster has more positives, so it's positively charged. When an object is charged, it creates a force. It can even attract powder. Rachel's using a similar idea to paint her bike, but this time it's the powder that's charged. The powder paint rubs against the sides of the gun barrel as it comes out and gets positively charged. Because the powder is charged, it gets attracted to nearby objects. Some of it even goes back on the gun, but most of it goes where it's needed, on the bike. So painting's a far less messy job. Oren has to turn his bike around to paint the back, but Rachel doesn't bother. The powder paint gets attracted around the back anyway. Oren's still messing about, but Rachel's nearly done. All she has to do is bake the powder paint to a finish. See you later. Rachel's metal bike was hung up on a metal hook that's connected to the earth. Why didn't the bike get charged when the paint stuck to it? It's because charges aren't always static. Inside an electric cable, there are 3 metal wires with coloured plastic insulation. Suppose you could see the electric charges. Positive charges can't move around, either in the plastic insulation or in the metal wire. But negative charges can move around, as long as they stay in the metal wire. Opposite charges attract. They like being together. Like charges would rather stay apart. They repel each other. Some rods go positive, some go negative. It depends what they're made of and what you rub them with. If you rub a Perspex rod on fur, the rod goes positive and the fur goes negative. They're oppositely charged, so the fur attracts the rod. But what happens if you charge up another Perspex rod? Both rods are positive, so they repel each other. It was the rod that was positive this time. Which way did the charges move to make this happen? When you blow bubbles, they usually just tumble out and fall on the floor. A Wimshurst machine uses friction to generate static electricity. Elaine's using it to make Matthew very negatively charged. So what happens next? Everything Matthew touches is negatively charged. Even the bubbles repel each other and fly off in all directions. Elaine discharges the machine to make it safe and connects Lakeisha to the other end. This makes Lakeisha positively charged. What happens this time? Matthew's bubbles repel each other, but then get attracted to Lakeisha. And the other way around. Elaine discharges the machine to make them safe again. This is another machine for charging things, the Van de Graaff generator. Elaine steps up and puts her hand on top of the metal dome. The dome becomes negatively charged. So Elaine does too. The negative charges in her hair try to repel each other, so her hair stands on end. Why does she have to stand on an insulated stool? And why does her hair go back to normal when she steps down again? The Van de Graaff's rubber belt winds around a Perspex roller. There are also some sharp metal points, almost touching the belt. The Perspex roller rubs against the belt and goes positively charged. Negative charges rush through the metal points and try to jump to the positive charge, But they hit the belt instead and get carried up to the top, where they jump off onto the metal dome. They want to get away from each other, but there's nowhere to go. There's a metal globe connected to the sharp points at the bottom. Moving it closer almost completes an electrical circuit. So what happens next? The negative charges are still trying to get away from each other, so they jump across the gap. It's like a tiny bolt of lightning. Lightning is nature's electricity, but is there a way to use its incredible power? Benjamin Franklin was an American who lived in the 18th century. At that time, America was still ruled by Great Britain. Franklin was trying to make electricity by rubbing things together, but he hardly ever got a spark. So he came up with a better idea. Lightning comes from thunderclouds, so Franklin reckoned he might be able to get electricity using his kite. He tied a ribbon to the bottom of the kite string with a metal key where they joined. Then he flew his kite up into a thundercloud, but stayed in a doorway so that the ribbon would stay dry if it rained. Thunderclouds are highly charged, and a metal spike helped to charge the whole kite, including the string. When the string got wet, the charges from the cloud could travel down towards the ground, because water can conduct electricity. The electricity couldn't get past the dry ribbon, but if Franklin put his knuckle nearby, an electric spark came from the key. He used the spark to charge up a special jar he'd made for storing electricity. Then he headed back to his laboratory to do some electrical experiments, but he was dead lucky. If the kite had been struck by lightning, he would have been killed. But he lived to fight another day, and went on to become one of the founders of a brand new country, the United States of America. You can make indoor lightning with Lord Kelvin's water dropper. You might find this a bit tricky the first time you see it, but it's only 4 metal buckets joined together with bits of wire. Water gets pumped up and sprayed into the top buckets, which have the bases cut off. Here's what happens. Suppose the top bucket has a tiny amount of positive charge. Positive charges are repelled back up the stream of water. So the falling water becomes negatively charged. This water collects in the bottom bucket, making it negatively charged as well. Then the water drips out through holes in the bottom. Now we know the charge on 2 of the buckets. The bottom left and top right buckets are connected by a metal wire, so the top right bucket also gets negatively charged. The water dripping through this bucket becomes positively charged. It collects in the bottom bucket, so that becomes positively charged. Bottom right is connected to top left, so the tiny charge you started with is increased. And because the water keeps flowing, all the buckets get more and more charged. two globes are connected by wires to the top buckets, so they get more and more charged as well. Until finally you get a... After a spark, the whole thing starts all over again. There's about 20 seconds between sparks. So that's how you make indoor lightning. But what should you do if a thunderstorm catches you outdoors?
Say, honey, looks like a storm's brewing.
Uh-huh.
So don't you think we should shelter under a tree?
A tree? Why, sugar, don't you know about lightning? That's the last thing you should do if there's gonna be an electrical storm.
Wow! How'd you know that would happen?
Let me explain, honey. Up in them big black clouds, there's warm air rising. About halfway up, it cools, forming different-sized ice particles. The smaller particles rise higher, rubbing past the big ones as they go. The rubbing makes them all charged up. The little ones are positive, while the big ones are negative. So, the cloud becomes negative at the bottom and positive at the top. Okay?
Yeah, I think so.
The negative charges try to jump to the ground, but they get distracted by little bits of positively charged air on the way down. That's why lightning zigzags. So now we have a very negative lightning bolt heading for the ground. And this repels away all the negatives from the surface of the ground, leaving it and everything on it very positive.
Oh no!
And the tallest, pointiest things around have the biggest concentrations of positive charge on them.
So the lightning goes there first, right? Bam!
Exactly. Bam.
So we better lie down, right?
Wrong. When lightning strikes, the electric current spreads out through the ground. So if you're in the open, you should crouch down real small with your feet together.
I feel awful dumb squatting here like this. But if you think it's the safest thing to do...
The best thing to do is shelter inside a car. Just don't touch any of the metal bits inside.
Got it? Can I stand up now?
You're safer inside a metal box or cage because the lightning bolts are attracted to the metal. This is a giant Van de Graaff generator. The electric current goes to Earth through the metal instead of going through the man inside. The best way to find out about static electricity is to do some experiments. But be careful. Electricity is dangerous.